Good day and welcome once again to a new series. I'm happy seeing your faces, and for those of you that will connect online and watch later, I'm happy that you are connecting to this channel. We are considering a new series this week, and from now onwards, we're looking at a new series. Okay, we just finished algebraic fraction. For those of you that may be wondering where we are coming from, we'll finish algebraic fraction. So do well to subscribe to this channel so that you can find links to all the series on algebraic fraction and mensuration. All right, so in this new series we are looking at, we are considering sequence and series, where we shall look at what is sequence, arithmetic progression, geometric progression, combined arithmetic progression and geometric progression, and their application. So please do well to stay tuned and stay connected in this new series we are considering. What then is a sequence? A sequence is a set of numbers governed by a well-defined rule. All right? The rule must be well-defined. For instance, I have a set of numbers here in case A, whereby the numbers are 5, 9, 13, 17, and 21. Okay? They constitute a set of numbers that are governed by a rule that we can find. So, how do we find the rule that is governing these numbers? Okay, when you study these numbers very well, it's covered that the first one began with 5. You will need to add 4 to the first one to get 9, the second one. And also, if you add 9 again to the second one, you will get 13. So what does it tell us? And you can keep on doing that till you get to wherever you want to stop. So this one, we call it the first term in sequence and series. Okay? We now say that each member of the set of numbers are called term. So if the first one, T1, the first term, is equals to 5, and we want to find the second one, the second term, which we can call T2, is equals to 9. But this 9, we want to observe what is happening to these numbers. All right, so when we add 4 to the first one, then we'll have the second one. It implies that the second number has its bearing from the first one, or origin from the first one. So we say 5 plus 4. Similarly, also, the third number, T3, the third term, can also be gotten from the second number, but since the second has its bearing from the first, it implies that you can also trace the origin of the third term from the first number by saying 5 plus, to get the second number, you add 4, and from the second number, 5 and add 4, you have 13. So you just simply add 4 times 2, which is 8. So we have 4 multiplied by 2. And the fourth term, T4, is equals to 5 also, in similar manner, 4 multiplied by 3. All right, when you examine this number, you discover that a sequence is formed. This is 4 times 2. 4 times 2, 4 times 3. This other one can be written in that manner as 4 times 1. And this first one can also be written in a pattern that resembles its fellow members of the family as 4 times 0. Now, what then is the pattern that is being formed? Because our interest is to generate a rule that is governing this set of numbers. So that in case we are asked what is the 256th term or what is the 10,000 term, we should be able to use that rule, the nth term, the formula that is guiding that family to generate the number of terms or the particular term that is of our interest. So the pattern formed here is that 5 is constant in all of them. So instead of writing T5, T6, T7, T8, and so on, we can just simply say the nth term, Tn, to represent the last term, the nth term, is equals to 5 is always appearing in all of them. So we say 5 plus, also appear in all of them. And each of them are 4 multiplied by something. So we now say 4 multiplied by what? Now we're talking about the nth term. When it was the first one, it was 4 multiplied by 0. And I will draw your attention that 4 times 0 is something as saying 4 multiplied by 1 minus 1. This one, 4 times 1 is something as saying 4 multiplied by 2 minus 1. Because when it is the second one, it is times by 1. So 2 minus 1, you have 1. When it is the third one, it is something as saying 5 plus 5 plus 4 multiplied by 3 minus 1. Okay? All right? So also when it is the fourth one, is something as saying 5 plus 4 multiplied by 4 minus 1. So we observe here that in all of them, when you consider a particular term, it is 4 multiplied by 1 less than the term you are considering. So since we are considering the nth term here, all right, so it's going to become 4 multiplied by n minus 1. And of course, when you expand, our Tn is equals to 5 plus 4n minus 4. And 5 minus 4 is 1. So we have 1 plus 4n representing the family formula, where n is not equal to 0. So this is now the rule that is applicable to this set of numbers in case A, where, for instance, when your n is equal to 2, you can check that when n is equal to 2, what do you notice? T2 is equal to 1 plus 4 multiplied by 2. And 4 times 2 is 8 plus 1 is 9. So you have our T2 is equal to 9, which is what we have here. I hope you understand this. All right, so we move to another set of numbers. All right. Similarly, we can generate the family rule for another sequence, such as this. All right, this is a sequence of numbers. They have been arranged sequentially, and there is a rule that is governing the way these numbers are being generated. So if the first term also here, if we call the first term here T1 equals to 31, let us observe what is happening here. We will discover that the second number to the 6 is 5 less than the first number. And the third number, which is 21, is also 5 less than the second number. That means it is 10 less than the first number. So the second number can be written as 31, remove 5. Of course, you have the second number, 26. And the third term, T3, is the same thing as 31, remove 10, which is as 5 multiplied by 2, and we have the third number, the third term. So rather than also writing for the fourth term, fifth term, sixth term, we can generate for the nth term by saying that Tn, representing the family rule governing this particular set of numbers, is equals to 31 minus something. This one is 5 times 2. Of course, this one can be 5 times 1, and this one can be minus 5 times 0. In similar way we did for case A, set of numbers in case A. So we have 31 minus 5, 31 appearing in all of them, minus also appearing, 5 appearing, but it is 0, 1, 2, and so what is it going to be? Is it going to be n or n plus 2 or whatever? What is it going to be? Now, this is when it was 3 here, we multiply by 2, less than 1 less than 3. When it was 2 here, multiply by 1, 1 less than 2. And when it was 1 here, multiply by 0, which is 1 less than 1. So we now say, since it's n going to multiply by 1 less than n, so we now say it's multiplied by n minus 1. And when you use your 5 to expand, our Tn is equals to 31 minus 5n plus 5. All right, therefore, the set of rules that is governing the numbers in case B will give us 36 minus 5n. We can check out whether we are correct. All right, we can check if we are actually correct. All right, okay, when n is equals to 3, do we get the third term here, 21? We'll now say if n is 3, T3 is equals to 36 minus 5 multiplied by 3. All right, 5 multiplied by 3. And that will give us 36 minus 15. Okay, therefore, our T3 is equals to 21. All right, so we come back to what we have here. Okay, this type of sequence, okay, in case A and case B, which increases or decreases by the addition or subtraction of a constant amount, is referred to as linear sequence or arithmetic progression, short form AP. Now we say it increases or decreases by the addition or subtraction of a constant amount. That means it's possible for it to increase or decrease by the multiplication or division respectively. So we're not talking about that. What we're talking about that every set of number, whether in case A or in case B, that is increasing by a definite amount, then such set of number is called an arithmetic progression. All right, so having understood that, now I must point your attention to the set of numbers in case A. When you consider a set of numbers in case A, which we have 5, 9, 13, 21, and so on and so forth, and that of B, because of the infinity sign that is attached to them, we don't know the last number. Okay, that means this set of number continues. Then we call them infinite sequence because they extend to infinity. Why set of numbers such as in case C here, we're having 3 over 4, 5 over 4, 7 over 4, then T, n over 17 over 4. You can see the infinite symbol appeared here, then ended with 17 over 4. This set of numbers, since n over 17 over 4, we call them finite sequence. Finite sequence. All right. Now we come to arithmetic progression. Having understood what is an arithmetic progression, that these are sequence of numbers which increases or decreases by the addition of a constant amount of number. Now, that constant amount of number is what we call the common difference, because it's actually a difference common to all the family members. Example, 9 minus 5 is 4. It's also common to 13 minus 9, which is 4. Also common to 17 minus 13. All right, 26 minus 31 is minus 5. And this minus 5 is also appears, it's common between 21 minus 26 to give us minus 5. And it's also common between 16 minus 21 to give us minus 5. All right, so, but rather than having different formulae, all right, for different set of family, as we have in case B, we have a family formula here, and also in case A, we have a family formula also here. Okay, now, both case A and case B belong to arithmetic progression. Rather than having different formula for different family of numbers, we can generate a general formula that will now be applicable to all the set of numbers that falls under or fall under arithmetic progression. So we now say, let the general first term be A. Okay, let the general first term be A. Let the general common difference, all right, let the general common difference be D. Okay, now in case A, the common difference is 4, while in case B, the common difference for case B is -5. So they have different common difference and different first term, which we have 5 and 31 respectively, which gave rise to the different rule that's applicable to that particular family in case A and a set of number in case B. All right, but since both of them fall under arithmetic progression, we'll not say, and any other set of numbers that also fall under arithmetic progression, we'll not say let the general first term be A and the general common difference be D. That implies from here we can now say that it implies that our first term, our T1, is equals to A. And our second term, okay, T2, when we add the common difference to the first one, just as if we add 4 to 5, we have 9. Okay, when we add the same 4 again to 9, we have 13. So we add the common difference to the first one. We're going to add the second term, which will give us A plus D. So this is the general second term. And the general third term, T3, is going to give us, when you add another A to the second term, another D to the second term, you're going to have A plus D, which will give us A plus 2D. So we have A plus 2D. All right. And also the third term, T3, will give us A plus the fourth term rather, and also the fourth term is going to give us A plus 3D. Okay, so instead of getting all of them, the fifth term and all that, so can I say that the nth term, Tn, is equals to, now, when it was the first term, it was A. Second term, A plus D, 1D. When we talk about second term, we said 1D. Third term, 2D. All right. Fourth term, 3D. Fifth term, 4D. 10th term, 9D. 100th term, 99D. Then the nth term is going to give us A plus n minus 1D. So this will now serve as the general formula for arithmetic progression. So this is the general formula for arithmetic progression, which can now work for all the set of numbers. All right. Okay, so here is the general formula. This is the general formula. Okay, general formula. Why each of these are the individual formula, or what we call the terms formula. Terms formula. Okay. The same thing is applicable to here. This is also the terms formula. I'll just write it as TF. All right, abbreviate that TF. All right, so examples. So let's apply to see how we use this in solving problems. All right. We're asked to find the 58th term. All right, so what do we do? What we do here is find your first term. A is equals to 4. Our common difference, our D, is the third term, 14 minus 9. Is the same thing as saying 9 minus 4, which we all have as 5. So if we check that, you discover that it will give us the same answer. All right. Why our n is 58. N is equals to 58. That implies using the general formula Tn equals to A plus n minus 1D. All right. That our T58, when we substitute, equals to 4 plus 58 minus 1 multiplied by 5. All right. So after simplification, our T58, okay, T58 is going to give us 289. Okay, 58 minus 1 is 7 times 5, we have 285 plus 4, we have 289. Alternatively, I have used the general formula here for all AP. I could also use the times formula for the A term. All right. So if the second term is A plus D, A plus 1D, third term is A plus 2D, fourth term is A plus 3D. That means 58 times is going to give us A plus 57D. I have also said that T58, okay, is equals to A plus 57D. Okay, when we substitute, we are going to have 4 plus 57 multiplied by 5. I will now also say that our T58 is equals to 289. So this is how we can apply individual formula and also general formula on AP. All right, example 2. The first thing we do is to examine the set of numbers to see what type of sequence are we having. 42 minus 47 is minus 5. 37 minus 42 is minus 5. So it is an arithmetic progression. So A, our first term, is 47. Why is it an arithmetic progression? Because the common difference, okay, is constant. So A is 47, and our D is not 47 minus 42. Please be aware that common difference is the second one minus the third one, the first one, or the third one minus the second one, or the fourth one minus the third one, and so on and so forth. Okay, so our D is 42, second one, minus the first one, 47, which is in as saying 37, the third one, minus the second one, 42, and we end up having minus 5. Okay, so the 16th term n is equals to 16. That implies that from the formula Tn equals to A plus m minus 1 multiplied by D, we can say that our T16 is equals to 47, which is our A, plus 16 minus 1 multiplied by minus 5. Okay, I will now have it as 47. Okay, 16 minus 1 is 15 times minus 5 will have minus 75. All right, therefore, when you simplify, you are going to have our T16, all right, to give us minus 28. So what that means is that when you keep on removing 5 from the first numbers and all that before the 16th term, by the time you get to the 16th term, you are going to have minus 28. The third example, okay, notice that whether it is increasing, the first example we took was an increasing set of numbers. Second example is a decreasing set of number, and in the third example we want to look at, it involves fraction. Okay, so this involves fraction. So is it an AP or is it a GP or none of the above? We shall find out. Okay, when we say that, when we do find our common difference, our D is equals to, all right, is that I will say 5.5, all right, minus 6.1/4, okay, which is it now 6.1/4, all right, minus 7. Okay, when we do this, we discover that our D will give us minus 3/4 in each case. So it's a constant difference. So we are dealing with an AP, all right, and our first term A. What is our first term? Our first term is equal to 7, okay, from the sequence of number given to us. And we are not asked to find the 12th term. That implies that our n is equals to 12. So using the same formula again for AP, because we are dealing with AP. So once we express an AP, we use the AP formula A plus n minus 1D. And notice how I have been writing the formula for every question. The more we write the formula, the more the formula sinks into your brain and subconscious that you will never forget it again. So T12, when n is equals to 12, is equals to 7 plus, okay, 12 minus 1 multiplied by minus 3 divided by 4. That will give us 7 plus 11 multiplied by minus 3 all over 4. When you simplify, you are going to have our T12 is equals to minus 5 divided by 4 as the answer. All right. Before we end this episode, let's consider example 4. All right. Now, is it only the terms they can ask us to find? Find the first term, find the 285th term, find the 16th term, and so on and so forth. Is it only 10 they can ask us to find? No. As long as this formula, the formula is involved, this formula here, okay, as long as that formula is concerned, you can be asked to find the terms, which is Tn. You can ask to find the first term, which is A. You can be asked to find the number of terms. Or you can be asked to find the common difference. All right, let's look at this example to close this episode. So, as usual, we identify our first term and other necessary parameters. Okay, our first term A is equals to 2. Our common difference D, our n, we don't know it. Okay, our last term Tn is equals to minus 1, 4, 1. That's our last term. And our D is equals to what? Our D is either I say minus 20, okay, minus 9, which will give me the same answer as saying when I say minus 9 minus 2, okay, minus 20 the third term minus the second term, or saying the second term minus the first term. So however you do that, you will notice that your answer is going to give us that our D is going to give us what? Minus 11. That will give us minus 11. Now, I'll point your attention to this. Why have I been doing this? Sometimes there are questions you cannot solve, okay, with the formula, which we shall see in the next episode. If you notice, each time I look for my D, I always express it in form of an equation, okay? Why I'm doing that is that I want to call your attention in the next episode that sometimes this formula that we have here, okay, this formula will not be able to solve some certain question, but you may need to form an equation using a common difference. All right, so what we know that our common difference does not change, okay? Whether I equate the second minus the first equals to the third minus the second, or the 20th minus the 19th equals to the 19th minus the 18th, we will still end up having the same thing. So that's an equation there that we can use. Okay, so we're going to see that in the second episode. That means you don't need to miss the second episode where we continue with further examples on this series. All right, so we continue what we are doing now. So when I say our formula Tn, our Tn is equals to what? A plus n minus 1 D. Okay, our Tn, the last term is 141. So when I say minus 141 as our last term is equals to our A is 2 plus, we don't know our n, we have to find it, then multiply by our common difference is minus 11. Okay, when this minus 2 go to the other side of your equation, becomes minus also. So we have minus 141 minus 2 is equals to n minus 1, okay, multiplied by minus 11. All right, minus 141 minus 2 will give us minus 143. All right, so we now say that that implies that minus 143 is equals to n minus 1 multiplied by minus 11. When we divide both sides to detach minus 11 from n minus 1, okay, minus 143 equals to n minus 1 multiplied by minus 11. Detaching minus 11 from that, we are going to have minus 143 divided by minus 11 is equals to what? N minus 1. All right. So when you do this, you discover that you're going to have 13, okay, equals to n minus 1, because minus we cancel our minus. And when minus 1 go to the other side of the equation, you have your n, n is equals to 14. All right. So This is where we are going to stop for this episode. All right, but before you go, I'm gonna leave you with a classwork. All right, so that is the classwork for my students and also my dear viewers. All right, so you practice the classwork at home, and of course, tell me what you have as your answer. You can send me your answer on the channel there, and I will also respond to you. All right, so we come to the end of this episode. Please don't miss out in the next episode as we're going to look at further examples on arithmetic progression. What we just did now is just an introductory course, just to familiarize, to introduce us to what is called a sequence and also what is called a linear sequence or arithmetic progression. In the next episode, which is the second episode of this series, we are going to consider more examples, and I hope you wouldn't want to miss out. All right? So please do not forget to subscribe to this channel and also like the video. And of course, we'll meet in the next episode, all right, for more questions on sequence and series. Until then, it is a goodbye from me, and thank you once again for watching and subscribing.